Okay, so this is chapter 2, part 2. So we're continuing on with our discussion of basic chemistry. And so we're going to start off, let me just move myself, by talking about molecules and compounds. And so in the last part of the chapter, we talked about matter and elements and atoms. And so we said that when we put two or more atoms together, so when two or more atoms chemically react and they chemically bond to each other, we form what's known as a molecule. And so in a molecule, the two or more atoms that are participating in this bonding can be of the same element. So for example, molecular oxygen, which is O2, which I have written right here. These two oxygen atoms are going to be bonded together to form a molecule of oxygen. And so it's one oxygen atom bonded to another oxygen atom. And so we have two of the same atoms. The same is true for atmospheric nitrogen. And so nitrogen is N2. So again, two atoms of nitrogen participating in this chemical reaction, in this bond. Okay. And so they can be two of the same element or atoms, or they can be made up of two different atoms. And so, for example, water is two atoms of hydrogen and an atom of oxygen, which is H2O. And so we have two different elements here, two different types of atoms. The same holds true for carbon dioxide, which is CO2. So again, one atom of carbon and two atoms of oxygen will participate in this bonding to form this molecule that we call carbon dioxide. Here's an example here, glucose, which is actually pictured over here on the left. Glucose is C6H12O6, and so 6 atoms of carbon, 12 atoms of hydrogen, and 6 oxygens make up this molecule. Salt, which is sodium chloride, NaCl. We have an atom, or actually I should say an ion, which we're going to get to it in a second, of sodium and an ion of chloride. And so we end up with sodium chloride, which is again common table salt. So all of these are examples of molecules, two or more atoms that have chemically reacted and have formed some type of a bond. A compound, on the other hand, is going to be a type of molecule that's going to be composed of atoms of different elements. And so we can say that all compounds are molecules, but not all molecules are compounds. Okay? And so examples here would be water, carbon dioxide, glucose, and salt, but we wouldn't include O2 or N2, so that's oxygen and nitrogen. Those would only be molecules. We couldn't consider them to be compounds. And so there's the difference there. Now, the ability of atoms to form molecules or compounds is dependent upon the atom's electrons. So remember from the last part of this chapter that it's the electrons that are going to determine the reactivity of an atom. And it's specifically the valence electrons, which we're going to get to on the next slide. Okay? Or actually soon. The slide after this. Okay. So I wanted to first show you again, what an atom kind of looks like, ignoring the subatomic particles, which would be in the atomic nucleus. So the protons and neutrons, we're kind of ignoring those. We're going to look at electrons. And so where electrons are in the atom. And so we know that electrons are going to be found outside of the atomic nucleus, orbiting in specific shells or energy levels, or you may learn about orbital theory, so in specific orbitals. For our purposes, we're just going to be looking at electron shells, and we will specifically be looking at, using Bohr models and Lewis structures. So in this example here, I'm showing you a Bohr model. So what is this? This is a model that is used to describe and show the arrangement of electrons in an atom. And so remember again, electrons are going to be found orbiting the atomic nucleus, residing in these electron shells or specific energy levels. Okay. Now, electrons have a natural tendency to want to be at their lowest energy level. And so that's going to be a level closest to the atomic nucleus. And so we have these shells, which in this figure look like rings, right? So this is the atomic nucleus. This is hydrogen. And so we can see the atomic symbol here in the center. This is how a Bohr model is built. We always put the atomic symbol of the atom in the center here. And then we have these rings, right? These shells. So this is the 1N, the 2N, the 3N, and so on and so forth. For hydrogen, it's really just the 1N that we need to be concerned with. We wouldn't even draw these other two if I was drawing a Bohr model. This first shell is the only shell that hydrogen is going to have because, remember again, hydrogen is number 1 on the periodic table. It has 1 proton in its atomic nucleus. The number of neutrons depends on which isotope of hydrogen we're looking at. But in any case, hydrogen is going to have 1 electron orbiting its atomic nucleus. And so it's only going to have electrons in that first shell, the 1N energy level. 2 electrons can fit in here. Hydrogen only has 1. If we were looking at, carbon, let's say, which we'll look at actually on the next slide. Carbon, remember, is number 6 on the periodic table, and so I would have a C here in the center. I would have 2 electrons in this first shell. And then if I went to my second shell, I have 4 electrons left, and so I would have 1, 2, 3, 4 electrons drawn in there. And that would be my Bohr model for carbon. I'll show you some more examples on the next slide. So that second energy level, or the 2N shell, is going to hold a maximum of 8 electrons. The first shell is only 2. The second shell is 8. The third shell, we're going to have holding 8. Okay? And as we go out away from the atomic nucleus, as we go up in atomic number, those shells can hold more. But this is the octet rule. So if we come back over here, the octet rule, atoms like hydrogen and carbon and oxygen, every atom that we're going to talk about, they're going to tend to either gain, lose, or share electrons to achieve a stable configuration similar to that of the noble gases. So if you remember back to the periodic table, all the way over on the right-hand side, that last column, group 18, they're called the noble gases. And so they're going to have full outermost shells. They have 8 electrons in that outermost shell. And so therefore they're stable. And so that's what atoms are trying to achieve. Okay. Now for hydrogen and helium, they only have that first shell, so they only need 2 to have full stable shells. And so hydrogen pictured here, it only has 1 electron in that shell. It needs 1 more, so it's going to have a tendency to react. Okay, hydrogen is going to react. It's going to bond in order to fulfill that first shell. Same thing with carbon. Carbon is going to have 4 electrons in that second shell. It needs 8, so it's going to tend to bond to try to fulfill that. And so again, some atoms will bond by sharing electrons, and some will bond by either gaining or losing. And we're going to talk about those different types of bonds. So again, the octet rule is a tendency for atoms to react in order to achieve stable electron configuration. And so for most atoms, that's going to be 8 electrons in their outermost shell. Okay, so here we go. So this is the periodic table, just a couple of the different groups. So we got group 1, 14, 17, and 18 in the first 3 periods. And so on this particular slide, I want to concentrate on valence shell and valence electron. And so the valence shell, that's going to be the outermost energy level or shell for that atom. And so if we look at the first period, which includes hydrogen and helium, their valence shell is the 1N. It's the first shell. That's all that they have, right? For period 2, their outermost or valence shell is the second shell, or 2N. Okay? The first shell is already full on these. The first shell is not their valence shell. It's the second shell. Oops. Okay, sorry. The period 3, it's their third energy level that is filling. Okay? And like we said before, if we look at group 1 atoms, Group 1, everybody here is going to have one valence electron. So there's one electron in that valence shell. Group 14 here, which includes carbon and silicon, they're going to have 4 valence electrons. So 4 and 4. Group 17 is going to have 7. So we've got fluorine here, 2, 4, 6, 7 valence electrons. Chlorine here, 2, 4, 6, 7. Okay. If we look at group 18, here's our happy group. These are our noble gases. So helium, with its one shell, it has 2. It's happy, it's stable. Neon, 2, 4, 6, 8. In that second shell, it's stable. And then argon, same thing. This is a typo. This should be 2 here. 2, 4, 6, 8. So 8 valence electrons, happy, stable atoms there. So if we look at, for example, group 14, we'll start with, carbon and silicon, they have 4 valence electrons, and all 4 of those electrons are what we call lone. They're not paired. And so both carbon and silicon are going to want to participate in 4 bonds. They want to fill their outermost shell, and so they need 4 more electrons. Atoms that have a medium number of electrons, so 3, 4, 5, 6 in that range, they're going to have a tendency to share electrons. Okay, and so we'll talk about what that means. Sharing is covalent bonding. We're going to get to that in just a second. If we look here at group 17, so we've got fluorine and chlorine. These guys have 7 valence electrons. So they have a tendency to grab an electron from another atom to fulfill their outermost shell. And so that's called ionization. So both fluorine and chlorine have a tendency to gain an electron and become negatively charged. So those are called anions. We're going to get to that in just a second as well. If we look at this first group, aside from hydrogen, hydrogen tends to form covalent bonds. It tends to want to share. But these other ones, lithium and sodium, having just a single electron out here in that outermost valence shell, they have a tendency to lose. So atoms that have low numbers of electrons tend to lose an electron. Atoms that are almost full, like fluorine and chlorine, they have a tendency to gain electrons. And then atoms that have a medium number of electrons, they tend to share. Okay, and so we're going to talk about covalent versus ionic bonding in just a second. But again, the number of valence electrons determines the stability of the atom. If it has a full shell, like hydrogen, helium, neon, argon, xenon gas, they're going to be stable, inert, unreactive. If they don't have a full valence shell, they're going to be involved in chemical reactions and chemical bonds. Okay, the type of chemical bond that they will form depends on the number of valence electrons in that outermost shell. Okay, so those were Bohr models. Let me take you back just a second. So again, these are Bohr models. So I'm going to be asking you to draw some of these. So you want to make sure you understand what they mean. So again, the atomic symbol goes in the center, and then you draw your energy levels around them, and depending on the number of electrons, you fill the first shell with 2, the second shell gets a maximum of 8, the third shell gets maximum of 8. We're not going to go above that. And so you want to make sure that you understand what a Bohr model is. Okay, it shows electron shells, it shows valence shells, and it shows valence electrons. Okay, another way to represent just valence electrons, so if you're not trying to put in all of the electrons into their energy levels or shells, you can use a Lewis dot model. And so here's an example of a Lewis dot model for oxygen, hydrogen, and carbon. The atomic symbol still goes in the center, and then the dots around represent the valence electrons. Okay, so you're not showing any electrons that are more inside. You're only showing the outermost shell of electrons. And so for hydrogen only has 1 electron, and so there it is. Oxygen has 6, but 2 are in the first shell. The other 4 are in the second, and so I would show them here as 4 dots. Pointer's being funny. 4 dots around carbon, okay? So carbon has 4 valence electrons. Here's oxygen. Again, I'm going to ignore the first shell, which holds 2. The second shell is going to hold 6. So I put them in one at a time. So I would do 1, 2, 3, 4. And then once I fill my 4 spots, now I'm going to double them up. 5 and 6. So we say that there are 6 valence electrons. There are 2 pairs and then 2 lone unpaired electrons. And so these 2 electrons are going to be the ones that participate in bonding. Okay? Carbon doesn't have any pairs, it just has 4 lone electrons. Okay, and so those 4 will participate in bonding. Okay. And so let's talk about bonding. And so elements or atoms are most stable when they have a full valence shell. So that might be 2 if it's hydrogen. If it's oxygen or carbon, it needs to be 8, okay, in that second shell. So how do atoms achieve that? They do this through bonding. And so what I have pictured here is an example of a covalent interaction. And so we've got 2 atoms of hydrogen and 1 atom of oxygen. And so hydrogen has 1 valence electron, each of them do, and oxygen has 2 unpaired valence electrons. These are going to be available for bonding. And so what's going to happen is this hydrogen is going to bond here to oxygen, sharing this pair of electrons. So again, this is a covalent bond. We'll talk about different types of bonding. And the same thing's going to happen over here. So this hydrogen is going to share oxygen's electron here. And so this is going to form another covalent bond. And so this is how we would draw it if we were doing Bohr or electron shell model. This isn't truly a Bohr model. And this is how we would do it if we were doing a Lewis dot structure. So this shows hydrogen's unpaired electron and oxygen's. These are going to bond. And so this red line here represents a covalent bond. And the same thing is going to happen on the other side of oxygen. And so we end up with H2O. So this is an example of bonding. And specifically, this is an example of covalent bonding where electrons are shared. Okay. Before we jump into ionic versus covalent bonding, I quickly wanted to just run through a chemical reaction just to make sure that we all understand what happens in a chemical reaction. So this is a process where one or more substances are going to undergo a chemical change. And that chemical change will result in the formation of new substances that have new chemical properties. Okay? During a chemical reaction, it's the arrangement of atoms that gets changed. And chemical bonds are either formed or they're broken. Okay? 2 or more atoms may end up being put together, so they're forming a bond, or maybe those bonds are broken, or maybe the bonds are just rearranged. Okay? So this is what a chemical equation will look like, and we're going to see these both in lecture and lab, so it's worth taking a look at now. And so to the left-hand side of this arrow, the arrow means yields. So to the left, we have our reactant molecules, and to the right, we have our products. And in this case, we have methane, which is CH4. Oh, I don't like how that's written. This H should be capitalized. In any event, so we've got methane reacting with 2 molecules of O2. So O2 and O2, which is oxygen, is going to yield carbon dioxide and 2 molecules of water. And so you should be able to count up the number of atoms here, and they should equal the number of atoms on the other side, right? So we're rearranging things, so we should end up with the same ratio of atoms. And so on this side, we have 1 carbon. On this side, we have 1 carbon. On this side, we have 4 hydrogens, and on this side, we have 4 hydrogens. On this side, we have 4 oxygens, and if you count them up, we've got 1, 2, 3, 4 oxygens. Okay, so they should be equal. Okay, nothing should be lost in the process. Okay, some reactions proceed in one direction, especially if the products are being used. Some reactions are reversible. Okay, some reactions will reach dynamic equilibrium, where the rate of the formation of products is equal to the rate of the formation of reactants. Okay, so for our purposes right now, I just need you to understand what a reaction is and the difference between reactants and products. Okay, and so some atoms are going to participate in ionic bonds. And so before an ionic bond can form, we have to form ions. And so let's talk about ionization, chemical ionization. And so to start off, let me define an ion for you. And so when we have an atom that either gains or loses one or more electrons, it's going to result in a net electrical charge. Okay? If an atom loses an electron, we're going to call that atom a cation. Okay, so we start off with a neutral atom with no charge. If the atom loses an electron, it's going to become a positively charged ion, which is going to get the name cation. Why positive? Well, if it loses an electron, it loses one negative charge or more. And therefore, it's going to have one or more positive protons in its nucleus. So there's going to be an unequal charge. It's going to be more positive than negative. Okay? The opposite is true if a neutral atom gains an electron. Now it's going to have an extra negatively charged particle compared to the positively charged particles in that atomic nucleus, so compared to the number of protons. So if an atom has more protons than electrons, it's going to have a positive charge. It's going to be a cation. If an atom has more electrons than protons, it's going to have an overall negative charge, and we're going to call it an anion. Okay? When atoms gain an electron and become an anion, the ending of the atom changes to "ide." So we'll see chlorine becomes chloride. Fluorine becomes fluoride. Okay, so we'll see that. Why would atoms do this? So why would an atom give up or gain an electron? Again, there's this natural tendency to want to achieve a full valence shell. So remember the octet rule. An atom will lose an electron or gain an electron or more to achieve a full, stable configuration of electrons in that outermost shell. Okay, so here's a nice example of ionic bonding. And so here we've got sodium, which is Na, that's the atomic symbol. Here's the Bohr model for sodium. If you count up the electrons, there's 2 in the first shell, there's 8 in the second, there's 10, and there's 1 in the third, that's 11. And so sodium is number 11 on the periodic table. It has 11 protons and 11 electrons. Here's chlorine. So chlorine is going to have 2 in its first shell, 8 in its second shell, and 7 in its third shell. It's number 17 on the periodic table. And so sodium is going to have a tendency to lose, where chlorine is going to have a tendency to gain electrons. And that's what's going to happen first. Okay, they're going to form ions. So sodium loses, you can see in red here, that single lone electron out in that third shell is going to be given up and given to chlorine. And so sodium becomes a sodium ion, a cation, positively charged. Chlorine gains that electron and becomes an anion, a negatively charged ion. And it's going to be called chloride. And so you can see that here's sodium, Na plus, right? It's positively charged. And here's chloride, Cl negative. Now, there's only one electron here. If, for example, with calcium, calcium tends to lose 2, so it becomes Ca2+. So the number of electrons gained or lost also goes as a superscript to the right of the atomic symbol. Okay, so first ions form. The ionic bond then follows. Okay, and so what is an ionic bond? An ionic bond is going to be an attraction between oppositely charged ions. Okay, typically ionic bonding occurs between a metal and a non-metal. And again, you can look back at the periodic table, the picture that I've given you in the previous part of the chapter, and you can look and see where metals and nonmetals are. Okay, so ionic bonds, they form, and what tends to happen is an ionic compound will form. Okay, so these are many ions attracted to each other. So you've got lots of ionic bonding happening here. And so if you look here, this is salt, common table salt. It's a crystal here. So they tend to form crystalline lattice type structures in which the ions are arranged in a repeating unit. And so you can see that here. Sodium is represented by the little yellow, and chloride is represented by green. And so they tend to form these solid crystal-like structures. Ionic compounds tend to have a high melting point and high boiling point, and they're typically solid at room temperature. Okay, those are the physical properties. They also tend to be good conductors of electricity once they're dissolved in an aqueous, watery solution, because what happens, when you drop salt into water, what happens is it dissolves. So what happens is the ions are separated from each other, and the ions are free to move around. They're no longer locked in that crystal, and they can conduct electrical charge. Okay, we say that ionic bonds are relatively strong, but they can be broken when compounds are dissolved in a solvent like water. So again, if you drop salt into water, those bonds break. Okay, so relatively strong, but when we compare them to covalent bonds, they're weaker. Okay, when sodium chloride, salt, does get put into water. So here we go, NaCl, this is sodium chloride, salt. When we add it to water, again, these ions will dissociate from each other. They come apart. So to dissolve, to come apart. And so we end up with sodium and chloride ions. Okay. Now, covalent bonds, very different. So in a covalent bond, there is no ionization. There's no ions that are formed. Covalently bonded molecules, if I put them into water, they do not dissociate. Okay. Covalent bonds are more common in biological molecules. So when we talk about macromolecules like carbohydrates, lipids, proteins, and nucleic acids, which we're going to be getting into pretty soon in the next chapter, they're going to have covalent bonds. Okay, we're not going to see ionic bonds. In fact, we're going to spend some time in the lab building biological macromolecules, and you'll see that they're all covalent bonds between the atoms, no ionic bonds. Okay. Covalent bonds tend to form between two nonmetals. So there's another way that you can define this. And here's the best definition of a covalent bond. It's going to be a bond in which a pair of electrons are being shared between the two participating atoms. Covalent bonding can be single, so one pair of electrons being shared, or double, there may be two pairs, or triple, there may be three pairs of electrons being shared. And you can tell that as we increase in the number of covalent bonds, those get stronger, right? The force holding them together is stronger when there's more bonds. The electrons being shared between the two participating atoms, the electrons might be shared equally, or they might be shared unequally. So we call a bond in which two electrons are being shared equally, we call that a nonpolar bond. So let me give you an example here. So we're going to go to methane, or we could look at carbon dioxide, but let's look at methane here. This is methane. It's CH4. You're going to build this in the lab in a few weeks. Okay, so it's one carbon, and that carbon is going to be covalently bonded to hydrogen here, 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 and here. So carbon has 4 valence electrons. It can participate in 4 covalent bonds. Hydrogen, each of them have 1 valence electron. They can each participate in 1 covalent bond. And so carbon is happy, right? It has a full valence shell because it's participating in 4 bonds. And each of those hydrogens is also happy. So this is a pretty stable molecule. When we look at the bond between carbon and hydrogen, again, it's a non-polar covalent bond. What does that mean? The electrons here are being shared relatively equally between both atomic nuclei. So it's a non-polar, okay? And that is because carbon and hydrogen have roughly the same electronegativity value, okay? However, if we were to look at water, for example, so this is another example of covalent interaction. This is a polar molecule. So what does that mean? So again, we have oxygen here sharing an electron with this hydrogen, and then over here sharing an electron with this hydrogen. Okay, same thing that we saw with methane. However, the electrons being shared, so if I look here, the electrons being shared here are not shared equally. So that's the definition of a polar covalent bond. So it's a bond in which a pair of electrons are being shared, that's the same, but they're not being shared equally. So why? So oxygen has a higher electronegativity than hydrogen. And so therefore, oxygen really has a greater pull on the electrons being shared. And so what happens there is that causes this molecule to have this molecular shape here where it's bent, right? And it has polarity. So what does that mean? Do you see these? This stands for partial positive charge, and so does this, partial positive. And oxygen is going to have a partial negative charge. So they're not ions. Hydrogen doesn't become positive and oxygen's negative. Hydrogen isn't just giving its electron to oxygen, it's still being shared. It's just being shared unequally. And so there are partial charges. This is really, really important for the next slide and also the next part of the chapter. Okay, so you want to make sure you understand the difference between a polar covalent bond, electrons are shared unequally, there is partial charge on the molecule, and non-polar covalent bonds, where electrons are shared equally and there is no poles, there's no polarity, no charge. Okay? Okay. That brings us here to water. Okay, so when we look at water, which we just talked about on the last slide, we said that in between the hydrogen and oxygen atoms of water, there is an unequal sharing of electrons, which creates polarity on the molecule. Okay, so here we go. We've got 4 water molecules. 1, 2, 3, sorry, 5, 4, and 5. Okay, so we've got 5 water molecules here. And what I want to show you here are hydrogen bonds, or really hydrogen forces. So what is that? So a hydrogen bond is a intermolecular force between partially positive hydrogen atoms of one or more molecule and a partially negative charge of an atom on a separate molecule, or it can really happen within the same molecule. In this instance, I'm showing you separate water molecules. Okay, so let's look at this. So here's my central water molecule. Okay, now because these bonds are polar here and here, polar covalent, we know that this hydrogen has a partial positive charge, and this oxygen has a partial negative charge, and this hydrogen has a partial positive charge. Now the same holds true for these other oxygen molecules. And so what's going to happen is the partially positive hydrogen atoms here and here of this water molecule are going to interact or be attracted to the partial negative pole, the oxygen, of this water molecule. And the same thing is going to happen over here. So the partial positive region of this water is going to be attracted to this partial negative charge on this oxygen. And the same thing here and here. And so each water molecule could interact with 4 other water molecules. And so these dotted lines, where's my pointer? These dotted lines represent hydrogen bonds or hydrogen forces. It's that interaction, that attraction, okay, between these. So it's an intermolecular force. Now, individually, hydrogen bonds are relatively weak, right? They can form, they can break, they can form, they can break. But when you have a lot of hydrogen bonds, so for example, holding the bases of a DNA molecule together, they're pretty strong. So they add up in time and space. We find hydrogen bonds, between water molecules. We find hydrogen bonds within protein structure. So when we get into protein shape, we're going to talk about secondary and tertiary folding, and that has to do, hydrogen bonds are there. And the same thing with DNA. When we look at DNA structure, the bases held together in the center of the DNA molecule are held together by hydrogen forces. Okay? Okay, so that's it for this part of the chapter. And the next part will be part 3.